I want to give you some sense of how MMC affects how parts get inspected with the use of a thing called virtual condition. So here is the basic idea. If there is an M in your geometric control, that is MMC, if there is an MMC, that means your inspector can use a fixed gauge. And fixed gauge just means it's a solid thing. It's not adjustable. It's just a solid thing, a particular size. They drop the part on, either it fits or it doesn't. So you can imagine how much time that saves in inspecting. There's no calipers and measuring and this and that. You just drop the part on, either it fits or it doesn't. So here on the left is a drawing of a block with a notch and 4 holes. And here is a position control. The position of the holes must be within this zone when the holes are at MMC. So our inspector has made an inspection tool simulating the datums with these 3 surfaces, simulating the pins, simulating the holes with those 4 pins, and then just as an extra note, see that notch there? That notch, well, let me see, this part, you could flip it upside down and still get it to fit in that gauge if you didn't have this little pin in that corner. And that pin is called a foolproofing pin. Very handy time-saving device for inspectors. If you have a way of putting foolproofing features in your part, do it. So here's one gauge. Here's another gauge over here. This is a plate with 6 holes on a bolt circle and then a hole in the center. The 6 holes have their position controlled at MMC, but the datum is also controlled at MMC. So what this M over here is saying is simulate the datum, the center axis of that datum hole, with a fixed size pin. So this virtual condition is a fancy way of saying what size is the gauge that you make. And it's a collective effect of the size, the MMC, and whatever tolerance you put on the thing. When you see an M, that means fixed gauge. I'm going to keep saying this because it's so important. MMC means you can use a fixed gauge. So here is an M with the datum, datum B. Datum B is the center axis of this hole. And because there's an M, it says we can use a fixed size gauge pin. Here is another part. It is controlling the position of these 4 holes. Datum B is specified at MMC. What is datum B? It's the center axis of this pin. And so when the inspector simulates that center axis in order to check this part, they can use a plate with a fixed size hole. And they'll just drop the part in there. If it goes in, it's a good part. Okay. So virtual condition is what ASME calls the size of the gauge. It's the size of a perfect mating part that will fit no matter what. It will fit in the worst case. And remember that ASME uses the term worst case when they mean the tightest fit, the closest fit. So virtual condition means it will be the closest fit. If you're tolerancing a pin or some other kind of external feature, then virtual condition is the size of a hole that pin will always fit through. So no matter whether the pin is bent and it's not straight, no matter whether it's out of perpendicularity, it's not at right angles, as long as the collective conditions of the actual pin will fit through that hole, that part will always fit interchangeably with any mating part that it's supposed to fit with. If the part is a hole, then the virtual condition is the size of a gauge pin that will always fit through that hole. Even if the hole is not straight, it's bent. Even if the hole is not perpendicular to the surface, as long as that fixed size gauge pin will go through that hole, it's a good part. By the way, you can only do this with features of size, things you can put a caliper on. So you can put an M and figure out virtual condition with the outside diameter of this pin because it is a feature of size. You cannot figure out a virtual condition with this flat surface over here because it's not a feature of size, nor with the circularity control on the surface of the pin. So it only applies to features of size. And here's the secret formula. If you have a shaft or any other external object, like a tab or a rail, if you have a shaft or external thing, the virtual condition size is MMC plus the tolerance. So external stuff, MMC plus the tolerance. If you have a hole or any other internal thing, like a slot, the virtual condition for an internal thing is MMC minus the tolerance. Here are a couple of examples. Here is, this looks like a pin. How do we know that? There's a diameter call out here and a center line. So here is a pin. This is a metric drawing, you'll notice. It has a size range, 12.2 to 12.6. Oh, we've seen this part before. And it has a perpendicularity control with a tolerance zone that is 0.3 in diameter. What is the virtual condition for this pin? You start with the MMC size of the pin, so the biggest pin, that's 12.6. Then you add the geometric tolerance when it's at MMC. Let me just back up. So if it's a pin or a shaft, MMC plus tolerance. Okay, MMC 12.6 plus tolerance 0.3. 12.6 plus 0.3 gives you a virtual condition of 12.9. That's the size of the hole in the gauging tool that the inspector will make. They will make a gauge with a 12.9 diameter hole. And to check these parts, they'll start dropping parts in there. And if they go in, yay. Here is the block with a hole. For its virtual condition, again backing up, for a hole, MMC minus the tolerance. Okay, the MMC of a hole is the smallest hole, 13.2, minus the tolerance, so 13.2 minus 0.3, here we are at the bottom. The virtual condition of this hole is 12.9 diameter. So your inspector is going to make a tool with a 12.9 diameter gauge pin. Here's a slot and a mating rail. This might be in a machining center, let's say. MMC for the slot is the smallest slot, so 0.368, minus the tolerance, 0.6. So the virtual condition of this slot is 0.362. Here's the rail. That's an external thing. MMC of the rail is the biggest rail plus the tolerance. So the virtual condition of that rail is 0.362. Look at that. So looking at the original drawing, you might say, oh man, these sizes are way far apart. You'll always have lots of slop, lots of clearance. But when you calculate the actual virtual condition for each one, you find out that at the worst case, their virtual conditions are identical, metal to metal. So very interesting. Let's look at this is a kind of a dorky looking drawing, sorry, I borrowed this from a book. So here's a block with a hole, metric again, and here's a pin that's supposed to fit in the hole. Virtual condition for the hole is smallest hole, 10.2, minus the tolerance of 0.3, so the virtual condition of the hole is 9.9. Virtual condition of the pin, biggest pin, 9.7, plus the tolerance, 0.1, virtual condition is 9.8. And so again, you might think, oh man, these sizes are way far apart. There will always be plenty of clearance. But when you calculate the virtual condition, you notice, at the worst case, you'll have a clearance of only 0.1 of a millimeter. Here's a sort of a drawing of those two. Virtual condition of the hole and virtual condition of the pin, and you just barely have a clearance at the worst case of 0.1 of a millimeter. The next couple of slides here are from ASME. This is an example from the ASME standard where they're illustrating virtual condition. So on this pin, this is metric, so this is pretty fine precision. The virtual condition of the pin is the biggest pin size plus the tolerance. So there's the virtual condition of the gauge. So your inspector will make a hole in their gauge tool that is that size. This slide from ASME illustrates how big a bonus tolerance you could add. In other words, if you made a part where the pin was starting to get towards the smaller actual size, you could be tipped, you could be out of perpendicular by this much and still have parts that would mate together. So just to review where we've been in this whirlwind tour, virtual condition is the size of the gauge tool that you use to inspect the part. It is the size of gauge that will just fit at the, call it, worst case. If you have a shaft or other external feature, virtual condition is the MMC size plus the tolerance. If you have a hole or other internal feature, virtual condition is MMC size minus the tolerance.